This is CPE 133. This is Introduction to Behavioral Modeling. This is from Chapter 6 of the Free Range Verilog Foundation Modeling text. So there are roughly two approaches to modeling digital circuits with Verilog. Essentially, there's a low-level approach, which we saw before, and that's data flow modeling. And although it's actually a form of behavioral modeling, but there's also a high-level approach, which we'll talk about in this chapter, which is essentially behavioral modeling. So this chapter, I put a disclaimer in there. It's a lot of definitions and pretty much very few examples. And now the vernacular, it's kind of hard to get used to, but it's actually super important, and it forms the basis of Verilog modeling. So although you can kind of get by with forgetting what some of this vernacular stands for and some of the names, and quite frankly I do too, there's certain rules you need to follow to ensure that your models work properly. So it seems like a big deal, but it's really not that big a deal. So I'm asking you just kind of go with the syntax, or go with the vernacular, and then it gets easier when you're actually programming. Not programming, but modeling, and that will be the next chapter. So once again, behavioral modeling, it's an approach to modeling circuits, and the idea is I'm not going to take a low-level approach in that I'm going to plop down the hardware to make my circuit do what I want. What I'm going to do is describe the behavior of my circuit. I'm going to just use the Verilog language to describe how my circuit should behave. Once I do that, I can send it off to the synthesizer, and the synthesizer will actually generate the circuit for me. So behavioral modeling, it's what makes any hardware description language, particularly Verilog, powerful. Essentially, it frees me from defining circuits at a low level. It allows the synthesizer to do some of the work for me. So this is both good and bad. Part of the problem is you're relying more on the synthesizer, which is a piece of software, it does a good job most of the time. You're relying on that software to generate the circuit for you. Now, the issue is that there's just certain rules you can follow. You don't have to follow them, but if you do follow them, your circuit's going to work. And there's not that many rules, but you really, really have to follow them. And so that's what this chapter is about. We'll see more of those rules in actually working in later chapters. So once again, this chapter has a lot of vernacular in it. So it's procedural blocks are essentially the heart of behavioral modeling. There's two types of procedural blocks. One's initial blocks, and one's an always block. Now, the initial blocks are not synthesizable. We use those typically in verification, which means simulating your circuit. So we'll see that in a later chapter. But always blocks are what we use extensively in Verilog, and that's pretty much about 95% of what you do when you're modeling in Verilog. So you got to understand these, and it's really, like I said, it's not that big a deal if you follow a couple rules, and we'll talk about those rules in a second. Keep in mind that this is digital design, and we are essentially taking modeling blocks and plopping them down and having those blocks talk to each other. So modeling using an HDL like Verilog is all about creating these modules or these blocks. So there's three ways to create a block. We've seen two of them. One is just to create a module. The other one is a continuous assignment statements. Essentially, a continuous assignment statement can be considered a block within a block. Essentially, it's a block within a module, and always blocks are, of course, another type of block. So these are three ways to define blocks or boxes in Verilog. And once again, digital design is about defining boxes and getting those boxes to talk to each other. So defining these blocks are essentially three different ways here. They're essentially functionally equivalent, and there's no real big advantage to doing it either way, according to the synthesizer. But according to humans who are trying to understand your circuit and you being human trying to debug your circuit, there are advantages to taking the most readable approach you can. And so I call that an intelligent approach, is making your code readable for humans. Synthesizer, no, doesn't care. You follow the syntax, it's going to be happy. But other humans reading your code, particularly you debugging it, it's important that you make it readable. So it's all about blocks. So the insides of always blocks, essentially they contain procedural programming statements. And so there's many types of procedural programming statements in Verilog. We are going to use only 2 of them. Now, so I encourage you to take a look at the other ones, but it's not going to be overly helpful in a beginning digital design course. So the 2 types of statements we're going to procedural programming statements that we're going to use are if, else statements and case statements. And keep in mind, it's just more like similar to this higher level language where a case statement is a special type of if else statement. So a lot more involved in that, but those are the roughly 2 types of statements. So when we use these if, else, and case statements, which are procedural programming statements, they have assignment statements within those. So there's 2 types of assignment statements in Verilog. So procedural assignment statements, there are blocking statements and non-blocking statements. And you can see the blocking statement here, it uses equal sign, and a non-blocking statement here uses this equal sign with a less than, which essentially I see that as an arrow pointing to the left. So it's common, you'll see that in other places in computer design as well. So let's continue looking at this. So procedural assignment statements, they're actually super important. They're just actually confusing, though it's really straightforward to deal with. And so we'll see those in examples in a later chapter. So just kind of hang with it now. We'll talk about it later in the context of examples. But I have just 2 examples sitting down here. Essentially, these assignment statements look exactly the same, except they use different operators. So here is the blocking operator, blocking assignment operator. Here's the non-blocking assignment operator. So the more involved, we'll talk about that later, like I said, in the context of examples. So these are some of the high-level rules here that, just to give you a flavor for, we'll talk about these pretty much continuously here. What you have in real life is a digital circuit. So this digital circuit is either combinatorial or sequential, or that essentially the components of that circuit. You can say, hey, that's a combinatorial block, that's a sequential block. Okay, so what you have in Verilog is different ways to model those blocks. So we can model those blocks using data flow or behavioral. So essentially you can model combinatorial and sequential digital circuits with either data flow or behavioral models. Okay, so keep in mind that data flow, once again, is primarily continuous assignment statements, and behavioral models are primarily always blocks. So the general rules, super general, and like I said, we'll talk about this later, is if you use continuous assignment statements, that means not using an always block. Use it for only combinatorial circuits. For always blocks, you're able to model both sequential and combinatorial circuits using always blocks, but when you do, for example, when you're modeling a sequential circuit, you are going to use nothing but non-blocking assignment statements. Additionally, you are going to incompletely specify the outputs in that circuit. So you are not going to provide an output for every single input combination. I know that's kind of out of the blue. We'll talk about that more later. So for combinatorial circuits, you are going to use specifically and only blocking assignment statements, and you are going to completely specify the outputs in that circuit. Once again, we will talk about that later. So the summary here, we are moving into behavioral modeling. It's one of 2 design approaches in Verilog, the other one being data flow modeling. And what we're going to do is use behavioral models to describe how our circuit behaves. Once we generate that model, we are going to rely on the synthesizer to actually generate the low-level circuit for us. So behavioral models, we are primarily using always blocks. The always blocks contain many types of procedural programming statements. We are going to use two, which is the case statement and the if-else statement. And inside those case and if-else statements, there are procedural programming assignment statements which can be of the blocking or non-blocking quality. And so, once again, that's all the vernacular for this chapter. We'll see all these topics in use in the next chapter.